second and third stages of the cerebellum. And so the stats will deal with your orientation. Brain palms, develop, posterior, middle, anterior, mid-brain, active, quick thigh, cerebellum. Forward. Stage 1, you recall, is the middle hindbrain vestibular flocculent nodular lobe. Just a small piece of the most primitive part of the cerebellum. Stage 2 has the primitive ventral spinocerebellar tract coming up bilaterally. And entering the cerebellum around the main sensory nucleus of the trigeminal to the superior cerebellopedoncle. This is the system that receives collaterals from all of the medium-sized fibers that are coming in the posterior columns and giving off secondary collaterals as the most rostrative vector ones going up into the posterior hindbrain to the nuclei and posterior columns in a conscious pathway, meaning in this case. The second system is the dorsal spinocerebellar tract coming from Clark's nucleus and ascending as the dorsal spinocerebellar tract and entering into the inferior pedoncle. So we have dorsal spinocerebellar tract and ventral spinocerebellar tract. Now the dorsal, of course, is coming from muscle spindles postsynaptically. We have a spindle out here, a large cell. Fibers come in also to the posterior columns, branch, give rise to intra-segmental monosynaptic reflex connections. And depending whether we're looking at a cervical or a lumbar segment, the cervical descending fiber will come down to the upper thoracic region, and the ascending one will come up into the posterior column, the lateral cuneate nucleus, and of course the lumbar ones have an ascending lateral that comes up to the caudal part of thoracic segments. But Clark's nucleus and the lateral cuneate nucleus change colors here. We have the double representation for arm spindles and the single representation of leg spindles coming into the cerebellum. And then, of course, we also have the main sensory nucleus of the trigeminal, whose fibers were the embryologically directing force that developed the superior cerebellar peduncle. And finally we have color chart here. we have the spindle system. Oh, buster, you screwed it.
That's from the main sensory nucleus.
That's main sensory nucleus, and that, of course, is receiving the medium-sized fibers out here in the trigeminal. With fibers that come in directly to main sensory nucleus, carrying all kinds of sensation except small fiber, large fiber. And then we have the large fiber system, whose cell bodies have a peculiar position of lying inside the central nervous system with a peripherally directed axon and right, that's spindles and jaw muscles, and a central collateral or something which gives rise to the fibers that come into the superior cerebellum. If you don't look at the cerebellum, we now have essentially everything's at pain temperature projected into the cerebellum. The most important of those being the spindle, the large fiber system. And that's why we have the spindle. It's not just to have monosynaptic reflex that keeps running around and jumping each time something comes in, but to tell the cerebellum as rapidly as possible that something has moved in the periphery. So whatever it is we're planning to do, to accelerate or to stop, we can begin to put the brakes or the gas on, as the case may be. Any problems on this stage 2? Spino-trigeminal cerebellar stage. At least on the afferent side. We should now take a look at how these come in. And for this, we'll take the Christmas tree pattern. The vermis. And a paravermis. Lateral cortex, flocculo-nodular lobe. And that, you'll recall, is obtained by just taking a piece of paper with the most rostral part of the cortex being represented here, wrapping it around, so that the most caudal part, nodulus, and the more lateral part of the flocculus, and the more lateral part paravermian, and the lateral cerebellar cortex. And we just flatten that out, and we get something like that. Which you recall is a 7-to-1 shortening of the rostral caudal dimension, but it's the more convenient pattern to play with. Any problems? So, we have to split the vermis. There's very little crossing of the midline. And what we find is that we have a tail, leg, arm, and head. Projection in the anterior vermis, which something like this: tail, leg, arm, head, like so. It's not exactly anterior lobe in the gross sense. It has a division up there. So the anterior lobe really has tail, leg, and arm, and the next lobe over is head. And then we have bilaterally, posteriorly, in the paravermian cortex, a projection that is tail, leg, arm and head, tail, leg, arm and head, like so. So we have a double or triple representation of the segments: coccygeal, sacral, lumbar, cervical, brainstem, in a fairly reasonable pattern in the anterior vermis and the posterior paravermis, with, and I'll call your attention to this head area in the center. And I could put that out a bit from the board for the paravermian cortex. Any problems? Okay, these, you take out folium, white matter, and Purkinje cell layer, and granule cells, and molecular layer. Back in Purkinje's day, they couldn't see much better than we can with our power H&E. Didn't have H&E yet, they had a nuclear stain. And they could see the grains of sand, granular. They couldn't see anything, so they called them molecules, invisible in those days. And here's Purkinje's. I've got Purkinje's illustration in the laser disc summary. The Purkinje cell has an axon that comes from white matter, go down to a deep nucleus and inhibit the deep nucleus. The afferent fibers that I put in blue along here come in, the white matter, and end as mossy fibers onto the short dendrites of the granule cells. Whose axon goes up into the molecular layer, branches at right angles to the board, and runs through the arborization of the dendrites of Purkinje cell. So this is the simplest path into the cerebellar cortex, through the cerebellar cortex, and back out. Okay? The deep nucleus for the vermis on each side is roof nucleus. Roof nucleus. Roof nucleus is going to project to the vestibular nucleus coming out through what peduncle? That would be inner. Inner, right. So it comes out through the inner to vestibular nucleus. Middle hindbrain structure overlapping into the posterior hindbrain region. Major descending connections to the lateral vestibular spinal tract. Down mostly to what kind of neurons, Linda? Gamma, small motor neurons, out to the muscle spindle. Particularly for what kind of muscles, Dave?
For the striated muscles.
Striated muscles. Okay?
Extensor gravity muscles.
Right. Here we have a spindle around the central part, and we have the striated muscle ends of the small muscle fibers in the spindle, and this is particularly of extensors. So the afferents to vestibular nucleus, Ray, are what for this system that we're talking about? Segmental afferents.
But the afferents are also from the spindles?
To vestibular nucleus.
Oh, from the
Primary sensory neurons out here.
in the it's not the otoliths.
It is the otoliths.
Oh,
So we have the otoliths gravity system. Afferents to vestibular nucleus, suprasegmental afferents to flocculonodular cortex as mossy fibers, to the inner peduncle, and the more laterally placed continuation floccular peduncle. Mossy fibers, granule cells, usual dendrites, usual axons, back down to the nucleus. Roof nucleus back out the same pathway, inner peduncle. And so we've amplified the ability of the vestibular nucleus to analyze what's happening. We've also stopped the system a little bit more by putting out information from the roof nucleus to adjacent reticular formation. So it's not just a purely private vestibular system, but it's mostly that. And we would expect the adjacent reticular formation to work fairly closely with that vestibular nucleus, having reticular spinal tracts. So what's going to happen to the Purkinje cell axons of the anterior vermis? Exactly the same thing. We're going down on the roof nucleus and go out inner cerebellar peduncle. So we have an overlap between the second stage afferents and the first stage efferents. So on the efferent side, it's going to affect predominantly vestibular nucleus and adjacent reticular formation, and predominantly gamma motor neuron system, predominantly extensor muscle spindles. But it's going to be modifiable by not only otolith gravity receptors, little hindbrains, but also by other spinal trigeminal segmental inputs to the anterior vermis. So one can show Purkinje cell here. This axon coming down. This being a vermian section. Coming down onto the roof nucleus. Just as we had blocking the nodular, I can say into the nodulus here. Purkinje cell sideways. Nodulus being this midline vermian structure. Any problems with the basic pattern?
What's the baseline output from like the vestibular spinal? I mean, is the how does the sort of concert of Purkinje cell inhibiting roof nucleus and then projecting out to the vestibular nucleus, is that sort of an increase that can you take off the cerebellum? Do they have more or less?
Right. There is a continuous tonic activity here. And when you take out the cerebellar cortex, removing the inhibition of the deep nucleus, you get an opposite effect. From taking out the deep nucleus. And now we have, I think, Ray?
So the Purkinje are inhibitory of the deep nucleus.
Let's take a break so we can listen to the music. I've been stalling things. To do that because it competes with everything else in my amplifier here. And I can't hear you.
So the Purkinje is inhibitory to the deep nucleus, and the deep nucleus is also inhibitory back to the vestibulocochlear?
No. It's excitatory as far as I know.
So if you come in and stimulate it through the modified molecular layer and stimulate the Purkinje cells, what you have to do is reduce the excitatory input back to the vestibulocochlear. So it doesn't seem like it would really amplify the signal. It seems like it would tone down where the vestibulocochlear
Well,
is.
I said amplify in terms of an anatomical sense. It gives you a broader field of interconnecting cells that most simply can be seen here when if you had just a purely floccular nodular vestibular cortex, there's no possibility of modifying that at all. It would, it'd be purely vestibular, purely otolith. And it turns out that that's not quite what you'd like to do. You'd like to be able to modify that. If I wanted, for example, to jump up or squat down, or if I move, do something against gravity, I've got to be able to compensate for that. So that when I drop down, I don't automatically spring back up again. One of us said, oh, you got to extend. I said, I don't want to extend, I want to flex. I'm a baseball player, I'm going to down and catch that grounder or whatever. So as you See, this is the cerebellum that we're presenting to you with this overlapping of stages is an ideal way, although it took 50 years or more for people to realize Raval's insight. Somehow it happened about 1940. That this was an ideal way of having the various stages of the cerebellum coordinated by talking to each other. And as you will see in a moment, stage 3 is going to come into everybody else. So I can voluntarily modulate the Vermian cortex to modify the activity of roof nucleus. So I'm not a purely reflex automaton, subject only to otolith stimulation.
That would be kind of rough. That would be kind of...
It would be, yes, it would be comparable, say, to the old 1940s neurophysiology of spinal reflexes, which said that the spindle acted for a millisecond or so, and so you tap, and you get a monosynaptic reflex, and now what do you do? And the spinal preparation, or deeply anesthetized preparation, that's all that comes through. But the real biologically important part of the reflex is not that, but the connections, particularly to Clark's nucleus and the lateral cingulate nucleus and to the cerebellum. That's why it's a very safe synapse at Clark's nucleus level. And it's a very heavy, numerically heavy number of synaptic connections. So it's not likely to fail. And it's a large cell and very large fibers are rapidly conducting. The whole system is built to get information up here as fast as possible. And it's essentially totally unconscious. But now having gotten to this part, and reminding you that the vertebral basilar artery comes up and supplies the superior cerebellar artery to the anterior vermis by clipping the basilar artery, by clipping the two carotid arteries, one makes the forebrain ischemic, totally ischemic, and the anterior cerebellum. And that provides the maximum removal of inhibition at the nucleus level, maximum stimulation of the vestibular nucleus, so you get a maximum cerebral rigidity, antigraphic response. More so than just surgically cutting across it. And of course, if you take out cerebellar cortex in general, you're not going to get incoordination, just laterally. But the limb is rather floppy. Reflex is rather hypoactive. With one exception, and that's the alcoholic, whose anterior vermis is out, Purkinje cells in particular. And so he's lost the inhibition, tonic inhibition of the nucleus, and had excess of vestibular activity, an excess of gamma activity. So he had hyperactive reflexes, stiff reflexes. So the alcoholic has a piece of the cerebral rigidity story. Any other problems on second stage of cerebellum? there is a piece left out here, of course, and that is we have two in the human intermediate nuclei. Symbolic form and logos, which in other animals are usually fused as an intermediate. And these, should be no surprise to you now, are going to receive the Purkinje cell axon from cerebellum cortex and are going to project out. I'll put in the median things here. Out the superior cerebellum peduncle, crossing, go to the opposite red nucleus. And crossing right back, rubric spinal tract, so that the second stage of the cerebellum has now its own relevant private output system. Which crosses to the opposite red nucleus, whose output immediately crosses back, and we end up on the same side. So we've kept the cerebellar input and output within a circuit. From the segmental association plate up into the cerebellum, out, briefly saying hello to the other side, coming back. So 90+% of this system is picture-lateral. Any problems?
That's through the superior peduncle.
Superior peduncle, right. Embryologically, an afferent tract, but then preempted, captured by the efferent systems. That's grossly dentate, comes in a moment, swamped. So it's essentially an output system.
Spinal tract ends where again?
Spinal tract. I forgot. That's a different place. You even know what the spinal tract ends on?
It should be primarily plexus, primarily, extremities.
Maybe I can find it. Well, it goes to intermediate cells, mostly of the deep association plate that will go to distal flexor muscles. That's what I have. So we got it together. They're wrapped together, right? So this is sort of the beginning of the parallel pieces of the cerebellar system that are opposite functions. The Vermian predominantly extensor, the paravermian predominantly flexor, and was one of the patterns that I think I mentioned the other day that Jim Sprague was able to take out first one and the other in the right sequence and modify the cerebral rigidity, increasing or decreasing depending on, it had about 6 or 7 operations that went out on it simultaneously, predictably increased or decreased. And so that's the basic pattern for the paravermian cortex, contrasting the vermian cortex, extensors versus flexors. So thank you for asking. There is another piece that I forgot to tell you about, the root nucleus. And that is that there is a little piece coming from the caudal root nucleus that goes out to the superior peduncle and crosses to the other side. It goes into the vestibular nucleus on the other side. This is the hook bundle muscle. And so we find that the two vestibular nuclei are reciprocally yoked together, largely through this crossed vestigial-vestibular tract that takes a slightly aberrant curve to the opposite side. So in general, we have flexors, extensors yoked together for balancing against gravity and rotation.
Which one's called the is that the Uncinate process or which one's the
That would be the Uncinate,
Uncinate hook?
So I think that's all we need for stages 1 and 2, and we come to stage 3. Stage 3 is going to be the forebrain stage of the cerebellum. And it's going to have 2 parts. A cortical and a deep nucleus. Sorry. And that's already sloppy enough. Let's try another one. Aqueduct and fourth ventricle, clitoris, behind the cerebellum, and forebrain. And I'm going to introduce the deep cerebral nuclei, exactly the same analogy with deep cerebellar nuclei. And avoid, more or less permanently, the word basal ganglia. The main reason for doing that is that basal ganglia are defined differently by almost every person who gets involved with them. And I got tired of that. I said, hell, we're involved with it. We're going to call them deep cerebral cortex. The main mass of forebrain fibers coming from all parts of cerebral cortex down through the internal capsule, cerebral peduncle into the pons, where synapse occurs, axons cross the midline, come into the cerebellum through a big peduncle, the middle cerebellar peduncle. Brachium pontus, you look at the base of the brain, you see the basis pontus, this big bulbous thing, and continuing from it directly into the cerebellum, big mass of white matter, middle cerebellar peduncle.
What's the synapse in it again? In the pons?
I'm sorry?
What is it that it's synapse?
This is the cortico-ponto synapse and pontocerebellar second neuron. Completely crossed. If you look at a section of the pons, in the basis pons, you will see vertically running fibers, corticospinal, corticopontine, and horizontally running fibers, the pontocerebellar fibers. In between those, you'll see islands of gray matter, which are the cells, nuclei of the basis pontus, giving rise to the middle cerebellar peduncle. And it turns out that there's a fairly sharp point-to-point projection of frontal, parietal, occipital, temporal cortex into pons. And a fairly sharp projection, point to point, from basis pontus into cerebellar cortex. Going to vermis, paravermis, and lateral cortex. And ending as what kind of fibers? Got it. Mossy fibers. Granule cells to Purkinje cells now, to a deep nucleus, which is a large structure of dentate. Big dentate nucleus out here. Off the word, of course. Cells give rise to axons that go out to the superior peduncle, cross, give a collateral to the red nucleus, and go up to the thalamus, specifically VL, which is one of the deep nuclei. So we have the dentate, out, VL, the collateral to the red nucleus, and from VL up to areas 4 to 6 of cerebral cortex. So we've completed a circuit. Cortico-ponto, the opposite cerebellum, the dentate, to the opposite again, back to the side, red nucleus, ventrolateral, and the cortex. So this is a system that's about 50-50. Forebrain opposite, cerebellum ipsilateral, to the extremity that's being controlled. So again we have with a cerebellar lesion, ipsilateral incoordination. Any problems? Well, let's consider the deep nucleus component. That fiber coming down the central tegmental tract. To end forming a capsule around the outside of the nucleus. Inferior olive. Whose cells give rise to fibers that come out of the hilum of this folded, but otherwise a simple plate-like nucleus with an outside of the capsule coming, fibers coming from the outside, inside, fibers going across the midline, 100% crossed, entering through the inferior cerebral peduncle, to go to all parts of the cerebellar cortex, vermis, paravermis, lateral. The ending is what kind of fibers? Coming in, the inferior olive, white matter, climbing around the dendrites of Purkinje cells. So this now is an entirely different system in terms of cerebellar cortical synaptology. And there are certain problems with this oversimplification because the number of cells in the inferior olive is nowhere near enough, by at least a factor of 7, to account for all the climbing fibers. One could postulate a branch, supply more than one Purkinje cell, but there's a discrepancy there. And also, if you take out the cerebellar cortex in the immature animal, without including olive, you will get climbing fibers. So there's another source of climbing fibers that hasn't been defined yet. But anyway, the current dogma is the olive provides climbing fibers, and then the Purkinje cell axons of the vermis, well, the roof nucleus to stage 1, the paravermis to the intermediate nuclei in stage 2, the lateral having the neocerebellar system all to itself now, hippodente, and back to red nucleus, VL, cortex. So we started in deep nuclei, gone down to olive, crossed the cerebellum, come down to stages 1 and 2 and 3, then take out to the opposite deep nucleus, not all of the ones that origin of the system, each one of them, and on the cortex as well. So we have again a circuit in which the one side of the forebrain controls the opposite side of the cerebellum with a double crossing. Crossing on the afferent side from the olive end, and on the efferent side, by crossing. In the dentato rubro-thalamic system.
Except for the stage 1, that stays ipsilateral for the most part.
Stage 1 is mostly ipsilateral, except for the hook bundle dorsal. Right.
So both the cortical part and the defrontal part go to all three stages. And is there a homunculus in the lateral part of the cerebellum as well?
Well, not that anyone's figured out yet. The result is you can take out a lot of lateral cerebral cortex. And the patient has incoordination for several months. It gets over. Taking out the dentate nucleus is not supposed to be such good technique. With one exception, and that seems to be if you've got a patient with Parkinson's. You can take out the dentate nucleus and improve the Parkinson's. Just as you can take out the L Parkinson's and improve the Parkinson's. It happens that the dentate is a tougher operation to do, so they don't do it very much. But half a dozen patients were done by very natural at Duke, I think it was, to prove that the systems were essentially the same. That takes us into the story of the basal ganglia, which I'd like to go for. We'll come back to it. Can't do it in 1 minute. Because all of a sudden you see we're faced with the problem of curing a basal ganglionic disease with a cerebellar lesion. And that becomes a little bit awkward because the classical distinction neurologically between Parkinson's and tremor rest. And the ability to touch his nose, back shaking. The cerebellar patient who can't touch his nose with the dam is an interesting neurological paradox. So any questions on stages 1, 2, or 3 of cerebellum?
So there's one thing that you may have said this. Is there a name for the nucleus where the cell bodies of central tegmental tract live?
Yeah, about 13. There's a very diffuse, or it's largely lobus pallidus, but most of the scattered basal ganglionic structures here contribute something to it. It's a very diffuse origin. Thank you for asking. Because it comes down to the inferior olive. And the inferior olive is a very nice point-to-point. Those particular parts of the cerebral cortex. And so it's as though the inferior olive is sitting there. Receive all kinds of bizarre information. Parsing out there. One can show that experimentally by taking out an immature cerebellum, take out a small piece of cerebral cortex, and then look at the inferior olive, and that part is atrophied, has disappeared. So-called Gooden's atrophy. But in general, you take out developing tissue, the afferent system shows more marked atrophy or even disintegration. than you do in the adult. The adult can show chromatolysins, but the cells rarely drop out. So this has been mapped out beautifully, again by Rodal and his collaborators, showing that the intraolive ponds have remarkably point-to-point projections into cerebellar cortex. And here we look at this great big mass of lateral cerebellar cortex, knowing that it's getting full of bulk, as the human brain is the biggest part, getting a lot of relays from particular places, widely scattered out cortex and deep nucleus. And yet we can't figure out what the hell it's really doing with all that information. Somehow these two structures, pons and intraolive, are, we've really only got a small part of the story. We must be doing something very particular that we haven't figured out. Now I just call your attention to the fact that midbrain, hindbrain, segmental structures have been obscured by these large suprasegmental paths, peduncle, basis prodis, interolive, and pyramid, with one exception, and that's the central tegmental tract, which is coming down through the reticular formation of the tegmentum. So it seems to be standing out as a major exception to the general rule that suprasegmental structures are going to be peripherally placed, obscuring the segmental apparatus. It doesn't really violate the principle because most of the reticular formation here is obscuring the localized segmental pieces, major motor association nuclei. But it is in that same general area, and not exactly where you would predict. So, problems, questions, comments? Tomorrow is Friday, I think, and so we'll take on the clicky line.